Okay, so today we're going to be talking about the areas of similar shapes. And so oftentimes you'll hear this referred to as the square cube law, or we're just specifically talking about the square part of that. And so we'll come back to that in a second as to why that's called what it is. But we're going to talk about the effects that scaling a shape up or down has on the area of that shape. You make the shape, the length and the width of a rectangle 2 times bigger. Does that make the area 2 times bigger or something else? So we are going to start off with just by considering kind of two rectangles here. We've got a 2x3 rectangle and a 4x6 rectangle. And if we think about the scale factor between these two, it's pretty easy to see on this one that it just got 2 times bigger. In fact, if we wanted to just write that down, in math, we'd talk about the ratio of the side lengths. And we could find that by either taking 4 divided by 2 or 6 divided by 3, because those sides correspond also. And either way, that simplifies to 2 over 1, or just 2. I'm going to leave it as a fraction for today, just because I want to see that generally this also works for fractional ratios as well, not just whole number ratios, like getting 2 times bigger. So if we take a look at the areas of these things, the area of this shape is going to be 6, because the base times the height is 2 times 3 is 6. And this one's going to be 4 times 6, which is 24. You'll notice the area did not get 2 times bigger. It actually got 4 times bigger. Right, because 24 divided by 6, the ratio of the areas, is 24 divided by 6, which is 4 over 1 if we simplify it. And so in this case, okay, that's cool. The ratio of the areas is bigger than the ratio of the sides. And we might be wondering at this point, is it just always going to be twice as big? Maybe something else is going on here. We'll look at a few more examples. But the reason it is not just 2 times as big is actually pretty simple here. If I were to take this shape and just kind of start filling in, and I can copy it a few times. Oops, I copied the wrong one. If I take this shape, let's do it this way. If I take this shape and I just start making copies of it to fill in, I can fill in 2 going left and right, and 2 going up and down. And so because it got 2 times bigger in both directions, it went times 2 this way, times 2 this way. Well, 2 times 2 is 4. And so that should also kind of lead us to the idea of, I made this 3 times bigger, it would be times 3 times 3, 9 times the area. So it's not always going to be times 2. The rule we're going to end up with here is actually that it's the ratio of the sides squared. And we'll keep exploring that and kind of convince you that that is actually what's happening. So we're going to verify with some other shapes here. This time, let's instead of writing this as our ratio as a big over small, let's do a small over big. So if I'm looking at my sides, maybe here, 3 and 9. Actually, we're going this way. 3. Oops, putting things in the wrong spot. If I look at my ratio of my sides here, 3 over 9 simplifies to 1/3. We could also do it as 24 over 8, which also simplifies to 1/3, because these are similar figures. Now, if I find my areas of these, just using my 1/2 base times height, this big one ends up being 108, and the little one ends up being 12. Well, what do you think 108 divided by 12 is going to be? If I take that ratio of the areas. Oops, I did small over big. That's one thing you got to do. Make sure you're consistent with what you're doing. All right. So if I find a calculator here off the side of my screen, there we go. If I pull in a calculator and go ahead and divide those, I've got 12 divided by 108, and it gives me a decimal, but I can turn it into a fraction, and it is 1/9. So if that simplifies to 1/9, and I can see 1/3 squared is 1/9. Right, because 1 over 3, if I square it, 1 squared is 1, 3 squared is 9. So that's squared. And we'll do one more here with circles, just as an example here. So I write my ratio of sides. I'm going to just go back to big over small. I think that's the way to do it. So I'll do 3 over 2 for my ratio of, in this case, it's actually the radius instead of the sides. But it doesn't really matter. The ratio here just refers to the length dimensions and the area dimensions. Then if I find my areas, remember, I've got pi times 3 squared, which is 9 pi. Here I'd have pi times 2 squared, which is 4 pi. And if I divide my areas, 9 pi divided by 4 pi, all that happens here is the 9 and the 4, or the 9 and the 4 stay because the pi's cancel out. And you can see again, 3 times 3 is 9, 2 times 2 is 4. We have just squared our ratio of our sides to get the ratio of our areas. And so what I would add in your notes here is this. It says if the corresponding side lengths of two similar polygons, or the radii of circles, are in the proportion of m over n, I guess I should probably use the word ratio there, m over n, then the ratio of the areas will be m squared over n squared. And one of those numbers could very well be 1. If the bottom was 1, we usually wouldn't write it. But that's our rule. That's the proportional areas conjecture. You'll hear it called the square cube law because the areas ratio is squared. Right? We'll eventually talk about the volume portion of this, which is the cube part. Right? So we'll do a couple examples here of kind of what this looks like to actually solve some problems. So I always want you looking for two things. I want you starting off with saying, okay, do I know the ratio, or can I find the ratio of the sides? Or can I find the ratio of the areas? If I can find one of those ratios, then I'm set. So in this case, I have two sides. I have 22 and 11. So I'm going to write a ratio, 22 over 11. And I'm going to always want to simplify that because I don't want to deal with 22 and 11. I'd much rather simplify it to 2 over 1 because that's an easier number to deal with. And then if I know the ratio of the sides, all I have to do is square it to get the ratio of the areas. And so 2 squared is 4, 1 squared is just 1. So my ratio of my areas is 4 over 1. And then I like to deal with these actual problems and solving the answer with a proportion. So the directions here actually say the area of the big triangle BCD is 64. Find the area of the little triangle XYZ. And so since I'm finding the area, I know I'm using the area ratio. So I'm going to write a proportion. 4 over 1 equals, this is the ratio of my area. I know it's in that ratio. This one's going to be the actual areas. So 64 is the area of the big one because I'm doing big over small here. And I don't know the area of the small one, so I'll do x. Then just like any proportion, I'm going to cross multiply. 4x equals 64. Divide by 4, and x is 16. So this one was 64, this one was 16, and if you look there, this is just times 4. 16 times 4 is 64. The area is 4 times bigger, just like we would expect. You might see some sort of an application like this. This one might be a little bit more interesting to you. Talking about pizza. So if I have two different types of pizza. A medium pizza is 12 inches, a large pizza is 16, and I want to know about the cheese. Well, the cheese is an area thing. So I can't just look at my ratio of 12 over 16 and talk about the cheese. That's the ratio of the sides. So I'm going to go ahead and write here ratio of sides, and really it's not sides, it's diameter, but that's the same idea here. Linear dimensions, length dimensions, and I'll go 16 over 12. And I'll simplify that to 4 over 3 because nobody wants to deal with 16 over 12. Then I'll go over here and write my ratio of areas. And I just know that I need to square that. Well, 4 squared is 16. 3 squared is 9. I know my ratio of areas is 16 to 9. Okay. From there, if I want to answer this question about how much cheese I need, I just need to decide, is cheese a length thing or is cheese an area thing? And since the cheese covers the whole area of the pizza, I want to use my area dimension to solve this. When I'm writing this proportion, I need to realize 3 ounces is on the medium, so that is on the small, and I'm trying to figure out how many ounces are on the large. So I just do 3 times 16. No reason you can't use a calculator on that. And if I go off to the side here and type 3 times 16, I get 48 equals 9x. And then I just need to divide that by 9 on my calculator. That's not going to come out to be a nice whole number, but that's no problem with the calculator. I get 5.3 ounces. It's 5.3 repeating, but that's fine. So even though the diameter is actually multiplied by 4/3, the cheese went up by more than 4/3. And the same thing happens with anything about the area. If you get a pizza that gets twice as big of diameter, you actually get 4 times as much pizza. That's why the large pizza is usually a better deal. Now, I just want to pull this question off to the side here and kind of see what you think about this. If I'm just looking at the crust in the pizza. So Domino's used to do this thing where they season the crust. They put this like flavored butter on there. It's probably really healthy. If I'm looking at doing the crust of the pizza, that is not an area thing. The crust of the pizza is just around the outside, the circumference. And so that is just a linear thing. If I was answering this question about the crust, I'd actually need to just use my 4/3 because this is a plain old linear dimension. And I'd set up my proportion like that. And I would actually get, I think, just 4/3, right? 4 times 1 is 4, 3x divided by 3. That should be 4/3 or 1.3 ounces. So linear dimensions, we use that linear ratio for linear things, circumference, perimeter, area things, cheese, we use our area ratio. And then let's just do one more here. So on this one, you can see they are telling us the ratio of the areas. So when I look at this, I see I need 2 things always. I need the ratio of the sides. And on your quiz, you're going to see this. You're going to see both. So this time I know the ratio of the areas is 9/16. And I want to go back because I'm actually asked to find one of the sides. Well, we know if we take the ratio of the sides and square it, we get the ratio of the areas. So the opposite is the square root. So I'm going to take the square root of 9, which is 3, the square root of 16, which is 4, and that's my ratio that I need to use because I'm talking about the sides. To write my proportion, 3/4. So this one is small over big already. You can see TR there is x, that's the small one, over 24. And now I can solve my proportion. 4x equals 72. Divided by 4, divided by 4. That's where I'm going to pull out my calculator. 72 divided by 4 gives me 18. And that's my side here. All right. So you're going to see a question like one of those 3, basically. Either you know the ratio of the areas and you have to find the ratio. You know the ratio of the sides. You need to find the ratio of the areas and set up a proportion to solve for an area. The exact opposite, you know the ratio of the areas, so you need to square root it and set up a proportion to solve for a side. Or maybe something more application-y, where you'd have to look at and say, okay, is the thing that I'm asked about, in this case cheese, is that a linear thing, a length thing, or is that an area thing? And then decide which proportion you would need to use based on that.